Just as in R2, we can find higher order partial derivatives. If we have already taken a partial of f with respect to x, we can then take a partial of that result with respect to y or x. I'm going to go ahead and write down the partial with respect to y. And this notation here indicates that we took a derivative with respect to x first. I should have said a partial derivative with respect to x first. Notationally, what we would do is we would say curly d 2f. And then first with respect to x, so that happens on the right in the what looks like the denominator, but it's not a denominator because it's a derivative. And then on the left, we'd say curly dy. So this is the second partial of f, first with respect to x, then with respect to y. So that with respect to x on the bottom, on the right, says that's with respect to x first. However, when we write it with the little subscripts, f, we would write it as xy. So f subscript xy, and that's how we denote it's with respect to x first. Now, it's probably frustrating and a little bit confusing. Y, in the first case, is the partial with respect to x on the right in the bottom of what looks like a fraction for the derivative notation. But in the second case, it's on the left, fxy. Really, it's whichever letter is closest to the function name, that's the one that happens first. And so when we write down partial or second partial of f with respect to y and with respect to x, that with respect to x is underneath the f. It's closer to it. With fxy, the one closest to f is the one that we did first. And so fxy means with respect to x first. If we want to find the partial with respect to x of a partial of f with respect to x, that would also be a second partial derivative. It is the second partial of f with respect to x both times, and so this looks like second derivative notation, right? Except the only difference is it's curly d's to indicate a partial, but like curly d 2f and then curly d x2. Using subscript notation, we would say fxx. This can be extended. We can talk about the third partial derivative of f, first with respect to x, then with respect to y, then with respect to x, writing those from right to left in the bottom part of the derivative. And using subscript notation, that would be fxyx. The first and the third of these, the fxy and fxyx, are called mixed partial derivatives. I can kind of have an idea of what a first partial derivative means, and we've seen a drawing on that one. A second partial derivative, whether mixed or not, we can kind of visualize those. I was asked one time by a student, what's the physical meaning of a third mixed partial derivative? I still don't have an answer for that. I don't know. But despite that, we can all know how to compute them. In our next example, we're going to find not third mixed, but we're going to find the second mixed partial derivatives. Our function is u is equal to e to the xy times the sine of y. I would like for you to pause the video and find the partial of u with respect to x and the partial of u with respect to y. Come back when you're done, please. For the partial of u with respect to x, y is constant, and so the sine of y is constant. So we have y e to the xy times the sine of y, just using the chain rule for the exponential portion. For the partial of u with respect to y, we have a function of y, e to the xy, times another function of y, sine of y. And x is constant with respect to y, so we end up with x e to the xy sine of y plus e to the xy cosine of y. Now I'm going to ask you to pause it again in a second here so that you can find the second partial of u first with respect to x and then with respect to y, and then find the second partial of u first with respect to y, then with respect to x. To make sure we're on the same page though, the partial of u with respect to x is the one that starts with the, okay, words are tough here. We already took the partial with respect to x that's the one we then take the partial of with respect to y. Likewise, the one we already took a partial of with respect to y, that's our starting point now for the second partial of u, first with respect to y, then with respect to x. So go ahead and pause the video and come back when you're done with this. The partial of u with respect to x is a product of actually three functions of y. So I'm calling y e to the xy. I'm just going to say that's the function s, and then the sign of y is t, but then s has two factors of y inside of it. So for s, we're looking at a product rule, so u prime v plus uv prime. But then for st, we're looking at u prime v plus uv prime. We end up with the second partial of u, first with respect to x, then with respect to y, is going to be e to the xy plus xy e to the xy, all that times the sine of y, plus y e to the xy times the cosine of y. For the partial of u with respect to y, we're looking at x times e to the xy sine of y, so that's a product of two functions of x. The second term simply has one occurrence of x, and so it's not going to use a product rule or anything. So the second partial of u, first with respect to y and then with respect to x, is going to be 1 times e to the xy sine of y plus x times y e to the xy sine of y plus y to the y e to the xy cosine of y. Now here's the point of the exercise, really. If we compare what we got both times, notice in the second answer we got the second partial of u first with respect to y, then with respect to x. And no, there's not really a faster way to say that. I mean, you could say like uyx, but then it starts to get a little confusing. But anyway, both of the first terms have a factor of the sine of y. So let's factor that out, sine of y, and we're left with e to the xy plus xy e to the xy, and then the second term is unchanged, y e to the xy times the cosine of y. Do you notice that the results matched from when we first differentiated with respect to x and then with respect to y? We get the same thing if we differentiate with y and then with respect to x. We can formally say that note the second partial of u, first with respect to x, then with respect to y, is equal to the second partial of u, first with respect to y, then with respect to x. This was not just a cleverly written problem. It actually is a verification in this case of something called Clairaut's theorem. That's C-L-A-I-R-A-U-T, Clairaut's theorem. And it says, suppose that f is defined on a disk D that contains the point AB. If fxy and fyx are continuous on the disk D, then fxy at AB will equal fyx at AB. In other words, second mixed partial derivatives are equal. We're not going to prove this result, but we're going to refer to it here and there.